Hey, what's up, guys? This is Chung here again. So today I would like to talk about this LeetCode problem 1392, longest happy prefix. It's a hard problem. I think it's a great one. Okay, so a string is called a happy prefix if there is a non-empty prefix, which is also a suffix, okay, including itself. Okay. Given like a string s, return the longest happy prefix of s, and return an empty string if no such prefix exists. Basically, it asks you to return the longest prefix, which is also a suffix. Okay, so for example, this one example one here, there are like a bunch of prefix. The prefix are obviously what? It's obviously the number of prefix that is obviously the number of the length, right? We have a L, LV, LEV, this, and okay, and so the LEVEL, so the number itself, I mean the string itself cannot be counted as a suffix as either a suffix or prefix. And for this problem, L is the only happy prefix. Okay, and for example, number two here, see there are like this ABAB is the longest one. Why is that? Because this is ABAB, this is the prefix, right? And this is also a suffix. That's why ABAB is the longest prefix and the suffix. Okay. And number three, similar, right? We have a prefix, which is LEET, and we also have the same suffix as this one. And here, if there's only one, it's empty because, prefix has to be smaller than the string itself, right? Keep in mind here, so it's the same string as a prefix or suffix. It's not the palindrome string. So which means that this A, B, C, C, B, A, this is the palindrome string, right? So basically the A, B, and B, A, they are like identical in the reverse order, right? But for this problem, it, we're looking for A, B, C, C, and A, B, not B, A. If this one is like for the B, looking for a palindrome, it won't be a hard problem. Basically, we can simply do a two-pointer solutions. We're starting from the beginning, and from end. We just whenever they're the same, we just decrease. We increase the left pointer, and we meanwhile decrease the right pointer, and then until there's no match, and then we simply return the answer, right? So that's that. That's going to be an easy problem. But for this one, it's a reverse order, right? Basically, they should have the same value. That's what's make this problem a hard one. And also, it's also because the constraints here. If the constraints is smaller, we can simply use the brute force, which is we try the prefix, which is the O of n, right? And then we compare with with the length of the prefix. We just for each of the prefix we compare if this prefix exists uh, starting from the end, right? That's going to be basically the O of n square. That's a brute force way. And with this 10 to the power of 5, this will TLE. That's why this is a hard problem. Okay, so to solve this problem in a better way, we have to know an algorithm called KMP. So now the next thing is I'm going to talk about what is the KMP algorithm. So there are like a lot of many videos online where you can talk about the KMP. So here I'm going to try to explain the KMP algorithm based on my understanding. So a KMP, what is a KMP? KMP. The name comes from, I think, three persons. I don't know their name, but that's KMP represents three person's initial. And this method is used to find a pattern in the string. So for example, let's say we have a string string is C D A C D A C D C. So this is the string, and we have a pattern. So the pattern is what? Pattern is C D A C D C. So this is the pattern, okay? And to find to check if this pattern exists in this string here, basically it means that if there's a substring in the S which is the same as the pattern. I mean, a naive way or the brute force way is that we start from each of the index, right? We loop through each of the index, and for each of the index, we compare. We compare the length of the same as the pattern. And then, for example, we start from C, we compare. So there are like six, right? The length is six here. So we compare CDACDA. Okay, it doesn't match, right? So we continue to compare from the D here. So DACD, we compare the next six number, six character. It's not a match, and then we move to A here. D is not a match. We do move to A. A is not a match. Then we move to C, and then C is a match, right? Because CDACDC is the CDACDC. So then we know, okay, so we find a match, a pattern, right? So, and as you guys can see here, every time we loop through, we compare the entire P here. Let's say we have a M here, so the length, this is M, and this is N. So the time complexity obviously is what? Is the O of M times N, right? That's the naive way. And the KMP way, KMP algorithm is to improve this one, from O of M times N to O of M plus N. So how does it do it? Okay. Mm, okay, let's say, so first, if you watch closely, when we compare the strings at the first time, CDACD, they're all matching with the CDACD. Only the A and the C is not is the I mean does not match, right? So the only reason we are having like this m times n time complexity is because we're going back, right? So once we move, once our cursor is at A here, next time when we're at D here, we will be calculating all those numbers from this D to A again. That's how we get this m times n time complexity. I mean, if we can find a way to not look back and to only keep looking forward, that will be ideal, right? But how can we do that? Cool. So since we have this kind of like patterns here, if you guys watch closely here, okay, so let's say we are at A here and we know, okay, A does not equal to C here. But if you guys can see here, right, so we have like a CD, right? So this C, D, and A, this one, or let's not look at the CDA here. Let's only look at CD here. CD. It's exactly the same as this CD here, right? And then since they are the same CD here and another CD at the beginning here, since we need to match from the beginning, right, of this pattern here, then we know, okay, this CD is the same as this CD here. So all we need to do is we just need to check if this A is the same with this A here, right? If they are the same, then we know, okay, we can keep going. We can keep going from here onwards. Then we have C, D, and C. We have C, D, and C, and then we find a match. So that's how the KMP algorithm works. Basically, so how can we know let's say when we have like a mismatch, how can we know which location or which position we need to go back to the original pattern string so that we can keep going forward? So we're at C here, right? I mean, we were at C here, and here is A. I think you guys may have already find out. So we have a CD here, and then we have another CD at the beginning. Okay. So basically now, if you look at the problem for this description for this problem, basically this is the prefix and this is the suffix of this CDACD. So all we need to know is that if we have like a mismatch at this location here, all we need to know is that what is the longest prefix as a suffix before this C here, which is starting from D here. In this case, is 2. Okay, since we have two, we have since we have the longest prefix as a suffix is 2, then we know. Okay, so we can simply start continue our matching at this location at the as the prefix and at the location after this prefix. Because why is that? Because we have already matching all of the numbers here. So which means that since we have matched the CD here, we know that okay, we have already have a CD before A because we have matched all the previous one, right? And since this C since the longest prefix as a suffix is 2, which means that there has to be another CD at the beginning of this pattern. Okay, so that since we have that information, we know that okay, which is cool, right? We can simply start after that prefix, and that's going to be our new start in this pattern. That's why we can just continue from A here, and then we continue from A, C, D, and C. And the end, we find that. Right? As you guys can see here, as long as we have that helper like array here that can tell us at each of the location what is the longest prefix as a suffix, then we don't have to look back. We will always so the cursor will always move forward. So that I mean there won't be a m times n here. So for traversing this s here, will only be a o of m here, right? So now the question comes down to how can we build that the longest prefix as a suffix at each of the location. Okay. So the way we're building it is kind of similar like a DP solution. And the way it works is like this. So we're gonna have like we're gonna call it longest prefix as a suffix. So I call it LPS. So this represents for longest prefix as suffix. Okay. And at the beginning, every place is 0. So we have a 0, 0, 0, 0, 0, 0. Okay. And then we're gonna have like a J and I here. So at the beginning, we have a J and we have an I. The reason they're not sticking together is that the suffix has to be the prefix and okay. So and the definition, sorry, the definition for this like LPS is the at each of the location. So for example, this one it means that at from 0 to I, from the 0 to I substring, what is the longest prefix as a suffix? So that's why we cannot start from the same index because a single string will not have the answer. That's why the minimum length for this LPS is 2. That's why we have we have a j and we have I here. And the way this thing works is that every time we just compare. We compare the I and j. If they are the same, then we just use the we use the j's index at +1 as the value of the LPSI. Okay, so let's say we have j here and we have I, right? So is this I equals to j? No, right? Then it's 0, right? So if they're not the same, then we move the I forward, and then now I is here. Is I equal to j? No. So this is also a 0, right? Now the I is here. Is the I equal to j? Yes, it's C. That's why we have a in here we're gonna have like j plus 1. So here we have 1 here, right? So if you guys just by simply looking at this string here, CDAC, so a prefix, the longest prefix as a suffix is the letter C. Okay. Now, so every time when we find a match, basically we'll move both J and I forward. It kind of makes sense, right? Because we're trying to find what's going to be the next. I mean, since we already have a 1 here, and now the next thing we're trying to find can we find a 2, right? So the way we're finding the longest length equals 2 is that we just need to compare the next number, the next letter after both J and I, which in this case, we're comparing D and D. That's why we're going to move J to here, right? And then we also move I to here. Still, again, we're comparing I and J. So they're still the same, right? So now we know, okay, we find a 2. That's why, uh, we are like, so this 2 comes from the index of J, the index of J plus 1. Because when that every time, so the j means that okay we find so the j means the we have find for the current I we have find the prefix starting from 0. Okay, that's why since the index is 0 base and the length is 2 base, that's why we do a j plus 1 here. Okay, and that okay, so we find a j and I here. Now again, since we're looking for, can we find a length equal to 3, which is the a and c, right? So this is the j, this is I. Are they the same? No. Then what? Then we'll go back. Then we'll go back to then the j will go back to the location of this LPS value here. Since the value for this location in the LPS is 0, so which means that so we are j is going back to here. So why is that? Because if the current I and j are not the same and the j is not in at the beginning, then we're trying to check, okay, if this after reverting this j back to its previously matched location, right, can we find a match? If we can find a match, we'll just use the value for j on that one. So in this case, it's gonna have like a c, since the c and c are the same, right? And the j is 0, that's why, and j plus 1 will be 1 here. So that's how we calculate this LPS, the longest prefix and suffix for each of the location here. Basically, from 0 to 3 we have 1. From 0 to 4 we have the longest prefix and suffix is 2, and from 0 to 5 is also 1, right? So it aligned with the visual observation. Okay, and yeah, I mean, okay, another example, right? So let's take a look at another example here. Let's say we have A, B, uh, A. Yeah, let's just use this one as an example here. And let's say so this is the LPS, right? We're gonna have like a 0, 0, 0, 0, 0, 0. So at the beginning we have J and I here. So J and I. I is the same as J. So then at this location we use the J plus 1, gonna be 1, which means that AA has one longest prefix as suffix. Okay. And once they are the same, we move both J and I, right? Because we're trying to find the next one. So now the J is here and I is here. Okay. And they are not the same. Since they're not the same, J goes back to what? Hmm. Okay, so J goes back to the values of the J minus 1, which in this case is 0. So that's why J will go back to here. And then we compare it again. Is I equal to J? No, it's not. Then it's 0. Okay, so now I is here, right? So when the I is here, I is the same as J. So now we have 1 here. And then the J and I both move forward, right? So we have A and A are the same. Now we have a 2 here, right? So as you guys can see, so here we have AA and AA as a prefix, also as a suffix here. Now the J is here and the I is here. So okay, so it's I and J are the same. No, right? They are not the same. So which means that they are not matching. That's why we will compare with the J minus 1 because we know J does not match with current I. Then we need to check if the J minus 1 matches with the current I. If it matches, then we know okay, we can continue from that J minus 1, which is exactly our case because since the J minus 1 is A and A is equal to this A here, that's why we can use this value here to populate here. Sorry, not this value. I mean, that's why we can use the value of the index of this J minus 1 to populate this one here, which will in this case is 2. Okay. Basically, that's how we calculate this array of this LPS. The value of this LPS represents the longest substring, the prefix as a suffix at each of the location. And with this LPS array here, when we calculate when we check the pattern, if a pattern exists in a string, we can simply use the value here. Right, like I said, and let's see, go back to CD A, CD A, CDC, right? We have a CD A, CDC. Okay, so we have a value here, so it's going to be 0, 0, 0, 1, 2, 1, right? So that's the LPS. This is the string. This is the pattern. So the way it works is like this, right? So we compare C, D. So we have an I here, right? And then we have a J here on this pattern here. So whenever they're the same, okay, we just continue move them until we find a mismatch, which is the I and J, right? So now I and J are here and they're not matching. So if they don't match, what do? We find the J minus 1 LPS value. So what's going to be the value? So the J minus 1 is here and the value is 2. Okay. So what do? We reset. Okay. We reset this J. We reset this J to here, which means that we can continue from this location. We can continue from this location and and uh, and continue our comparison here. And now we're comparing if this I is equal to J, yes, right? And then we keep moving. C is the same, D is the same, and C is the same. And as long as the J is the same as the length of P, then we find the answer, right? So as you guys can see here now, since here at S here we only do a O of M, and to generate the LPS is O of N, right? That's why the time complexity in total is O of M plus O of N. Cool. So I think that's enough for this KMP algorithm. And how can it help with this problem? Actually, for this problem, we're only using this LPS. We don't even need to apply this pattern matching here, because all we need, as you guys can see here, so this LPS is exactly what we're looking for. So here we're looking for the longest prefix as same as a suffix for the whole string. So which means that the last answer, the last number in this LPS is the number we're looking for. Okay, and we just use this number to get the first this number string, and that will be our answer. Okay, so a few examples here. Let's say AB, 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 right? Okay, let's see we have a A, B, A, B, A, B, right? So if we have follow our LPS here, so this is the J, this is I, right? Is I and so this is 0, right? This is also 0, right? And now the I is here. I is the same as J. That's why we have 1 here, right? And then the J is here, I is here. I and J are the same. Then we have this J plus 1. So remember J is the index, right? So we have 2 here, right? And then we keep moving. Here A and A are the same, and then we have 3 here, right? So because J is here now, J is 2 plus 1 is 3. And again, in the end, we have B and B. So now when this one's the same, we move J to here and I to here. Again, they're the same. That's why we have a 4 here. And as you guys can see here, 4 is the longest prefix as a suffix for this string here. And that's going to be our answer, basically from 0 to 4. 2 to 4. Right? And this is the our answer, A, B, A, B. Cool. So the implementation is pretty straightforward, but the intuition or the algorithm is not that easy. Okay, that's why we have 3 persons in this algorithm, K and P. All right, so LS, right? And then we have a LPS. And at the beginning, everything is 0 here. Okay, like I said, right? So at the beginning, we have J equal to 0, and And then we have another like a second pointer, which is I from the index 1 to n. Okay. So how are we going to implement this, right? So like I said, we're gonna have like so first thing first, while the si is not as the sj, so that's gonna be the first check here. If it's not the same and j is greater than 0, what do? We set this j to LPS j minus 1. So why we're doing the while loop here? Because if the current I and j are not the same, okay, then we will be like I said, setting this j to the j minus 1 value in this LPS, okay, and then we'll continue comparing the s and j. If they're still not the same, we'll set this again until either we find a match or the j was reset back at the beginning of our of the pattern of this string here. Then we stop. Otherwise, we continue doing it until we find a match. Okay, if we only do it once, I mean, after setting this j to the LP at j minus 1, the si and the sj there could still not be the same, right? And then in that case, we have to keep going, right? Otherwise we will not be finding a valid match later on. Okay, so once we have figured out that part, then we check if the si is the same as sj. If they're the same, then we do a LPS I equals to j plus 1, right? And then we move the j forward. So why are we checking this one? Because let's say if the j was moved back to 0, and we still need to check that, like the a b a c maybe. Yeah, like for example this one, right? So we have 0, 0, 1, right? Now we're comparing b and c, right? So b and c are not the same, right? And then that's why, and the value for LPS value for b is 0, and we move it back to a here. Okay, and then we compare. We compare if a is the same as c. And they are not. That's why we have 0 here. We only do this when they match to each other. Okay. So, and since later on, all we need to do is we just need to LPS minus 1. That's going to be the last value for that. Okay. If I run the code, okay, sorry, longest prefix as suffix. Okay. Run the code. All right, accept it, submit. Cool. So, yeah, there you go. That's how we use the KMP, part of the KMP algorithm to solve this problem. Pretty tricky. Actually the reason I'm talking about KMP is there's another more difficult problem. We'll be using the KMP. So that's why I decided to talk about this problem as a warm-up for that problem. I think most likely I'll be talking about that problem tomorrow. Yeah, we'll see. But I know the KMP is not that easy to know, but just try to understand it and remember, and try to remember the algorithm and the concept behind it. Okay. Okay, cool, guys. Thank you so much for watching this video and stay tuned. I'll be seeing you guys soon. Bye bye.